I'm really happy to be here. This topic of thermal comfort and how we design around it is an area that I've been interested in for a long time, and I've been working on this as long as I've been at Arup. So I'm excited to get to present this to you today. Usually I do present this in person, so I'm used to people interrupting with questions, and that's totally fine. And I've got a couple of slides that are sort of interactive. So, please do feel free to chime in with any questions that you might think of as we're going through this. I'll just kick off with a little bit about myself and about Arup if you're not already familiar with us. We're a firm that acts globally trying to design a better built environment. And here in Boston, I work with a team of about 100 people in our office. We've been in the Americas for about 37 years with 16 offices, so it feels like we're growing pretty quickly. And we have a diverse set of offerings. This is just what we do in Boston. And technically, I sit on the lighting team, although I think as you'll see as I go through this, that the work that I'm doing goes far beyond that and touches on a lot of occupant experience in and around buildings. Um, this session is approved for AIA Health and Human Health and Wellness credit. Mandatory slide. I try to keep this at an introductory level. There is plenty of jargon. If I say something that you don't understand, stop me. I'll go back and correct myself. If you don't like it, I'm supposed to give you email addresses to reach out to. So there's my email address right there, and also our CEU coordinator. If you do like it, you can also email us. That is also certainly encouraged. But let's go ahead and dive into it. So this is the title that I work in under the AIA credit, Thermal Comfort for Diverse Populations. Really, what I try to do is look at how we can make spaces more comfortable to a broader group of people. And I've got a couple of thermal images here that are they're just from a party that we had at our office about a year ago, looking at people, enjoying drinks in the office. And you can start to tell things about people and how they're feeling just based off of this simple data. So, for example, the woman in the top center, who was our CEO at the time, her nose is cold compared to the rest of her body, and this woman down here has colder lips. And so you might stop and think, well, what is it about those people and what they're doing right now in that moment that's making them look and feel that way? I don't know. Sometimes somebody, jumps in and has an idea and raises their hand. So feel free to, think for a moment about what might be happening there.
When I was playing around with an IR camera with me and my wife once, I put my hand on a wall and it left a
Yeah.
long handprint, but she has Raynaud's disease, so her fingers are constantly cold. So when she put her hand on the same wall, she
Mhm.
sapped the heat out of it. So I think, some people just have colder extremities.
Yeah, exactly. So you can be seeing the blood flow through people's skin and their faces and how much heat that blood is moving out to the extremities of their body. In this case, there's a fairly simple explanation. The woman up here is breathing through her nose, and this woman is breathing through her mouth, and that changes the way that heat is distributed through their face. And in academic settings like University of California, Berkeley, there are now researchers who are really looking at people with that level of granularity to understand how that transfer of heat through different parts of the face and body affects thermal comfort. What I'm going to be talking about today is a bit more broad strokes, but still really trying to think about how we can use that kind of information to design for better comfort. So I do have a few learning objectives. I'm going to talk, first of all, a bit about history. How did we get to where we are now with our ideas about thermal comfort? And in some cases, where did they go wrong and why did they go wrong? Um, and then we'll talk about some different determinants of comfort that might be a little bit more useful for understanding different people's experiences. And finally, how we can use that in design with a few case studies. And I like to start with this example. So this is the Chicago Auditorium building by Louis Sullivan. Um, you can go here to enjoy a show or some music or something. If you want to pay a lot of money for your seat, I like to ask my students where they would sit, and you know, they typically tell me, down at the bottom, close to the audience. And if I ask them where they would end up if they didn't have a lot of money to pay for their ticket, they, tell me that they would be up somewhere in the rafters in this upper balcony. And so I ask them about the comfort. How does it feel to be down here with the cool air that's falling down versus up here with the hot air that's rising up to the top, all of the electrical equipment and mechanical equipment that's generating heat up here, the sweat from the audience that's carried with that heat up to the top. Um, and I point out that those seats that you're paying less for, they're also less comfortable. Now turn that around and go back to Shakespeare's Globe Theater. If you didn't have a lot of money in Shakespeare's day, where did you end up sitting or standing? And they'll point down to the bottom and say, well, back
Near to
then, yeah, you'd be right up by the stage. And if you had money, you sat far away in the box seats in the back. So the point that I make here is that what you're paying for in those settings isn't proximity to the stage and the actors. What you're paying for is comfort. And about a century ago, with the development of air conditioning, we started to bring that comfort into spaces. We took, you wouldn't go to a movie on a hot day in the summer before air conditioning because it would be unpleasant. But thanks to air conditioning, a movie theater became somewhere that people wanted to be on a hot day. And so we got this multi-billion-dollar industry of the summer blockbuster. And along with that, we see these headlines that seem to pop up every year, as we go into summertime, asking us whether or not our buildings are sexist. You know, uh, are we creating buildings that some people can enjoy more than others? And there was a interesting study, sort of an anecdotal study, but an interesting study that was done by University of California, Berkeley, a few years ago. It mined Twitter back when it was possible to mine Twitter, and it looked for tweets that mentioned both the word office and some indication of temperature, feeling hot or cold. And it also examined those tweets by the apparent gender of the user based on their Twitter handle, in order to see when were men complaining about temperature and when were women complaining about temperature. And it found that not only did men and women complain in different amounts, but they also complained at different times of year. So they were responding to different temperatures occurring that they found to be uncomfortable in the places where they were working. And so this is, no, it's an anecdotal piece of evidence that tells us that there are differences in the way that different people experience temperature that may be based on gender. So, when I started working at Arup, I got interested in this topic and I wanted to understand, well, where did our scientific basis for thermal comfort come from? Why do we design the way we do? And then, since I'm an engineer, I also want to know, how can I improve it? And so I went back and, just doing some historical digging. This is an interesting illustration, comes from 1939. It is a description of the climate in different parts of the world and where you could live comfortably without climate control. And so the black areas are the areas that would be comfortable. The gray areas require some climate control. And as you move out of those into the white areas, you need more and more um, manipulation of the temperature in order to make yourself comfortable. And what you can tell right away is that this is based on a European sensibility of what is comfortable. So Europe is colored all black, and then when you get outside of that, there are just very narrow parts of the world that they consider comfortable. And it's also labeled with when those areas were settled by Europeans, or as they describe it in the illustration, when climate control was introduced to those locations to make them comfortable. And you can kind of see the effect of that colonization. So these are pictures of what look like nice, English buildings, except that they're not in the UK. These buildings are in India. And so you have this idea that English settlers were coming out to other parts of the world, building the type of building that they were used to, and then realizing that that building wasn't comfortable in other parts of the world the way that it would have been comfortable back home. And this, there was design guidelines that were put out about how to make these spaces more comfortable for Europeans and why this was necessary. And if you go back to these sources, like the Heating and Ventilation and Air Conditioning Guide, which is the forerunner to the modern ASHRAE handbook, they had ideas that were quite frankly racist. So this one is suggesting that the reason that that people in other parts of the world seem to be comfortable in temperatures that Europeans were not comfortable in was a result of biology and specifically the fact that maybe they were less active than people coming from Europe. And of course, we now know that that's wrong, and we've developed a better sense of what causes people to feel comfortable and not comfortable. And really, the next scientific advance was the result of war. So, in World Wars One and Two, we were sending our boys, and they were all men, sending them to other parts of the world. They had to be, ready to get off the boat and fight as soon as they arrived. They had to be able to perform peak conditions, so we need to know how to dress them. And so we started to develop these terms like the MET for metabolic rate and CLO for clothing insulation that allow us to quantify what we need to do to make them comfortable. And these were uniquely American units. We didn't want to go out and use kilowatt hours. Germans were using those. Didn't want to use British thermal units, too British. So we came up with an American unit to describe American comfort. And that's what we now find in sources like the ASHRAE Handbook or ASHRAE 55, which are geared to, tell us what should make people comfortable. And I'm not here to promote ASHRAE 55. I think that there are plenty of problems with it, but I do think it's useful to understand what ASHRAE 55 tells us. So I've got a bit of a quiz. Feel free to unmute and shout out some answers. But ASHRAE 55 says that there are some factors that affect our thermal comfort. So does anybody have an idea or want to guess what some of those might be?
Relative humidity, probably
That's
external.
one of them. Yep. It's an external factor, relative humidity.
Outdoor air temperature,
Air temperature is quite an important one.
humidity,
Yeah. So there's a couple of them, right? So there's the internal factors that I just mentioned a slide ago. They're metabolic rate and clothing. Those vary from person to person. And then there are the external factors. There's temperature, humidity is on there. Also radiant temperature, that's the temperatures of surfaces around us, and airspeed or wind. And then more recently, they added to this list with what are essentially a set of fudge factors to tell us when these factors alone don't predict comfort. And so those are things like temperature asymmetry. So if we feel heat coming to one side of our body and cold coming to another side of our body, draft, and that's specifically air movement around our ankles, vertical radiation in temperature, so our head being hotter or colder than our feet, floor surface temperature, so contact with other surfaces, and then anything that causes variation over time. But what ASHRAE gave us were these scales, the predicted mean vote and predicted percentage dissatisfied. And what this basically says is that if you poll all of us in one room and you ask, who's feeling cold, who's feeling hot, and you take an average of our feelings, that's your mean vote. And if you do it based mathematically on the factors I listed earlier, that's your predicted mean vote. And then you can take that over to this predicted percentage dissatisfied scale. And so in this case, it's an example where we're probably at a vote that's between slightly warm and warm, a value of about 1.7 on that scale. You follow it up and it tells you that at that point, about 60 to 70% of people in the room will feel unhappy with their thermal condition. And I've tried this out with my students, and it turns out that this is a pretty good predictor of the thermal comfort of American college students. Now, if we look more broadly, though, or we try to drill into that and say, well, how are individual people feeling? It turns out it's not such a good predictor. So here's some actual data, room temperature recorded on the horizontal scale, the comfort vote going from cold at the bottom to hot at the top on the vertical scale, a nice diagonal line showing the average of how people should feel based on temperature, and then dots showing the individual votes. And what you see is that there are a few outliers there, actually a lot of outliers. There are people who report feeling warm when the temperature is relatively cool, and people who report feeling cold when the temperature is relatively warm. And so how do we start to design for those people, the people who are outliers, who really make up, most of the people who respond to the survey are not here on the diagonal line. They're not average. And so I thought this question was really interesting. How did we choose that average line, and how did we decide that, that temperature of about 25 degrees centigrade or 76 degrees Fahrenheit was really the optimal temperature where everybody should be feeling neutral? And there's this nice little study here. It took similar polling data. Um, it had kind of a bizarre thing. They were looking at performance, so how well people performed, and the optimal performance is when this is taking a mathematical derivative. So when the slope hits zero, that's the peak performance. So this is where they say that everybody should be comfortable, and they arrive at that 72 degrees Fahrenheit. And it's based on sort of a mathematical curve fitting into this whole set of data. And again, the folks at University of California, Berkeley kind of took this and said, well, how do we know that this is the right way to do this? And so what they tried to do was fit various different curves to that same data and look at the statistical error in those different curve fits. And basically what they found was that they could put all these different types of curves through the data, and they were all equally good, or you could say they're all equally bad. They all describe the spread in this data with roughly the same accuracy, which means that you could basically pick any temperature to be the optimal temperature according to that method. Well, so that doesn't really give us a lot of confidence in why we should be using 72 degrees Fahrenheit. So we've got to keep looking to understand, how did we get here? And I think that at the end of the day, you can say that a lot of what we understand about thermal comfort now, and really a lot of our scientific basis for what thermal comfort is, comes from an effort to make this man comfortable. And not only was it a scientific achievement that we could make him comfortable, but I would argue it was a point of American national pride that he was comfortable. And if you recognize him, you'll know right away why that was the case. And if you don't know who he is, it might sound completely weird, but who knows this man? Who is he?
Is that Neil Armstrong?
You're exactly right, Michael. That's Neil Armstrong. I've got another picture here for those of you who didn't recognize him the first time. But yes, for the first time, we were sending people somewhere where we had no anecdotal evidence about what it felt like to be in that place. And we had to make sure that when he got there, he didn't freeze, he didn't bake, he was able to perform in peak condition. And that meant we needed computer simulation to tell us if that would work. And for the first time, we had computers that were capable of doing that. And they used very simple models of the human body, basically dividing the body into pieces, each of which had a temperature, and they could conduct heat to each other and receive heat from the environment. But this was a mathematical model that told us what the temperature of his body would be and how comfortable he would be. And over time, these models have gotten more complicated, looking at different tissues in the body, looking at the flow of blood through the body and how it conducts heat or convects heat into the body, and looking at how clothing does things like retain heat and retain moisture around the body, which give us a much more accurate picture now of how people feel under different external conditions. But there's one thing that sort of stayed the same between all of these, and that is the assumptions that we make about the person we're studying. So this is the original height, weight, and fat content from that original study for NASA. So that describes Neil Armstrong's body. He's right here on these scales of typical American height and weight. So average height, below average weight, extremely lean, very little fat on his body. He is a fit individual. And as we take that forward and see what other studies have looked at and how they've given us more accurate measures of thermal comfort, they have all made very similar assumptions about who they are designing for. So there's a lot of inertia in the ideas that we have about who this individual is that we design for. And so the argument that I make about this now is that when we continue to use this data, and again, these teams were, not trying to hide who they were working with. The same thing, they're designing for or studying healthy, physically active men. But when we design for those circumstances, we are now designing buildings for astronauts. And so I tried to make that point, and the folks at Arup thought it was a good enough point. They hired someone to walk around in a spacesuit so that we could take some pictures and try to drive home that this is what we're doing right now. But when we look at ASHRAE and what ASHRAE is asking us to do, it asks us to identify at least one, but we only need to identify one representative occupant for any space. And we make them representative based on metabolic rate and clothing that they wear. And we don't pay attention to factors like age, gender, and build, which affect how people experience spaces. So let's take a look at what those assumptions do for us. So this might look a little bit familiar. This is that U-shaped chart from the predicted percentage dissatisfied scale. Tells us that when we have neutral conditions, most people are happy, and when conditions get very cold or very hot, people get unhappy. And this is the prediction. And now we have a lot of survey data. So this is based on 65,000 surveys that ask people right here, right now, are you comfortable? And what I've done with this chart is I've taken the bottom row and color coded it into, when people are predicted to feel neutral, well, you can see how they're actually distributed. And when people are predicted to feel cold, wait a minute, half of the people in that bucket still say that they're feeling neutral. So that means that, our predictions coming from the PMV scale are only about 34% accurate. If we rearrange people, put them in the buckets based on how they actually feel and not how we predict them to feel, well, then we get this nice U-shaped curve again. It tells us that, when people feel neutral, they're happy. When people feel cold or feel hot, they're unhappy. That's in air-conditioned buildings. If you open the windows, people feel differently about the environment. People are more tolerant of hot and cold temperatures if their windows are open than they are when their windows are closed. Also, this works for offices. In people's homes, we have more tolerance for hot and cold temperatures. Maybe it's because we feel more freedom to put on a sweater. Maybe it's because we feel more responsibility for our utility bills. But for whatever reason, we don't complain so much about temperature at home as we do when we're at work. It also matters where you are in the world. So again, this curve, which was based on studies of college students in the United States, works well for people in temperate climates. If you take a look at people in Europe, in continental climates, preferences are different there. And if you take a look at arid climates or tropical climates, we also see different reactions to temperature there. So it can be difficult to take the assumptions that we have about people's thermal experience from the US and export that to other parts of the world. So, what are the factors that we should be looking at, or what does cause people to feel different about thermal comfort? And one factor we've already touched on is gender. So there are some cultural impacts here. We tend to see that men and women wear clothing with different amounts of skin coverage, which can change how they perceive things like drafts and direct sunlight. They have different amounts of insulation associated with them. That is more apparent when people are wearing formal attire. It's less apparent in people's day-to-day outfits. But there are also physical differences based on body size, which affects how much heat we produce internally, based on body fat content, which affects how quickly we can radiate that heat or get that heat out of our bodies to the environment, and based on core temperature, which is affected by hormonally. Age is another factor. So we understand now that children are more tolerant to low temperatures than adults, and I've experienced that this winter with how difficult it is for me to get my kids into coats when they go outside. We also know that as people age, they lose some of their ability to regulate their internal body temperature, and we see that reflected in their perceptions of the environment around us. And that can be especially dangerous as they age and are exposed to hot temperatures where they may not be able to adjust their core temperature quickly to compensate for that. Um, and then there are some factors built around location and ethnicity. And one of those I can point out socioeconomic differences. The map that you see here is a map of a practice called redlining. This is showing the Boston area and labeling some areas as having been less desirable and therefore harder to get loans to buy houses in, and therefore tended to concentrate people in less advantaged socioeconomic groups. And houses built in those areas tended to have less access to air conditioning, might have housed people who were more likely to be working outdoors with more exposure to the outdoor environment. And people living in those areas might have had more barriers in access to healthcare or an ability to speak English. And those differences carry through to today, even though redlining is no longer a legal practice. But if we expand more broadly and look beyond, just a single city to the entire world, we're also starting to understand now that there are differences in how people experience temperature, what their preferences are based on geography. And so the chart here compares the preferences that Americans have for temperature with preferences that Chinese and East Asian people have, and we see that in China and East Asia there are preferences for warmer temperatures. And that's just based on data that we have. So this map is showing in the color code the amount of survey data that we have on thermal comfort from different countries, and you can see that there are large portions of the world shown in white where we just don't have that data. So we aren't really able to make judgments right now on, are these differences that we see because East Asia is unique, because America is unique, or is it just that every part of the world is different in their preferences? And now these factors become very important as we start to see increases in temperature based on climate change resulting in excess heat mortality or heat deaths. And these headlines are unfortunately becoming more and more common as extreme heat becomes the leading natural disaster cause of death. And here's just a bit of data to show what's happening. This is coming from Texas. I think this was published in 2024, so it's about more than a year old now, but saying that 3 of the 4 highest numbers of heat-related mortalities in Texas had come in the last 3 years. And if we try to understand why that's happening and where it's happening, and I ask my students, well, where do you think those deaths happen? And first they guess that those are people who are going out and hiking in the wilderness, or they're, people who are living on the street or something. But really, they're people living in buildings, and especially elderly people living in older, unair conditioned buildings in disadvantaged neighborhoods. And if you look at these two maps, the one on the left is showing the instance of the urban heat island in Boston, and the map on the right is showing the results of those disparities as a result of redlining, the locations of various disadvantaged communities today or more vulnerable communities. And you can see a lot of alignment between those poorer neighborhoods and the areas that are more affected by the urban heat island. So what can we do about this? How do we start to understand these people's experience in order to design more effectively with them? One thing that we can do is to work with a feels like temperature. So you may be familiar with these from things like looking at wind chill or heat index in the weather report. A feels like temperature tells us what people perceive the temperature to be like based on the amount of heat that's entering their body, both from air temperature, but also humidity, radiation from the sun, and other factors. And for outdoor environments, we tend to use something, a feels like temperature scale called the Universal Thermal Climate Index, or UTCI, which allows us to take all of those factors that were involved in the ASHRAE calculation of comfort and put them together and tell us, will people feel comfortable in these conditions? And this is useful for working outdoors. When it comes to working indoors, what I've tried to do is really move beyond the ASHRAE scales to look at something that we call advanced thermal comfort modeling. And what we do here is we take those thermoregulatory models, like the ones that have evolved from the NASA program, and combine them with psychophysiological models. So the complicated word, what it really means is how people feel about their temperature. And so you see this woman here. She's doing a sort of an office-based task. She's wearing a bag of air, a bag of cold air strapped to her back. And while she does her task, she's filling out a survey to describe how she feels about that environment. And through these different studies, we came to understand how people would react, what their emotional state is based on having heat or cold applied to parts of their body. And we can put that together with a thermoregulatory model in order to predict how people feel in different environments. And so this is a tool that we developed at Arup. It's called our Advanced Comfort Tool. It allows us to develop journeys as people go through multiple different thermal environments, say adjusting temperature, wind speed, and so on for each of those environments, and also looking at clothing and activity level and seeing how those will apply or remove heat from parts of their body. What I really like about this tool, though, is that we can start to adjust parameters for this person, make them female, change their height and weight, and see how individuals respond to those different conditions, and then overlay the experiences of different groups of people to see how an entire population might react to these conditions. And this is then a design tool where we can start to adjust parameters and see what we could do to make the entire population comfortable as they go through this transient progression of different thermal experiences. And so we've now been able to use this in a few different projects. So I'm going to give a couple of case studies and talk about how we can design with the thermal comfort of populations in mind. And I'll start with some work that we did recently for the new MIT College of Computing. The architect here was SOM. And in this space, there's a large glass atrium that you come into. It's facing south. And so, of course, there are questions then about, what is the effect of sunlight entering this space? And so you could take a look at someone coming in on a hot day. It's hot outside. They come to the interior right away. They feel that blast of air conditioning. It feels cool and relatively comfortable. Maybe they hang out in the lobby for a bit of time and then head up to their office. And this is based on Neil Armstrong's physiology. So we're assuming now that Neil's tenured professor at MIT and this is his day. But if we want to expand that out and look at how other people feel in this environment, we see that there's a not insignificant number of people who enter into that air conditioning and they feel cold right away. And that's especially going to be the younger women coming into the space. So maybe the solution now is we take away that blast of air conditioning. So let's try to design more passively. We remove the air conditioning, and now there's a different group of people, mainly the older people in the space who are starting to feel hot in here. And so our next step is to say, well, maybe the problem is direct sunlight. So let's put in shading. And when we put in shading, now we've made a more comfortable experience for a greater number of people in the space. And so perhaps this is how we want to be designing as we look at that space. Here's another example, MIT College of, or this is the MIT Student Center. Similar question, they were remodeling this student space. This is what was there before. It looks quite different now. And we were looking at, well, what is the effect of that curtain? Would we need to put in a more solid curtain? Can we have a more sheer curtain that lets more light in? And how do people feel as they're studying in this space, after having come into some air conditioning, walked up a few flights of stairs, so they're already perhaps predisposed to feel hot as a result of their elevated metabolic rate. How long does it then take them to cool down? And by putting in different types of fabric here, we can change how quickly they cool down. And it turns out that we can even have some fairly sheer blinds and still promote thermal comfort. And at the end of the day, in this case, it turned out that visual comfort would be the driving factor for selecting those blinds and not thermal comfort. We can look at this spatially as well. I'll just bring in some work that we did for the new EXP building at Northeastern University. In this case, there's a spatial question. So this is the top floor of the building. The president has a new office that's right over here. And we wanted to understand how the big storefront glazing on this building would affect thermal comfort and how close to the glazing you could get before you would start to regularly experience these periods where direct sunlight would lead to hot feelings. And it turns out that there's a small area along the glazing. There's also, might be difficult to see, but a little patch under a skylight here where you start to get that warmth happening more often. But it tells us that we can use the mechanical system in this building to provide comfort over most of the space, especially the spaces where we knew that complaints would matter. The building also houses some chemistry labs. And so here we really got into some really granular analysis. This study was actually because of concern that was raised about whether or not the fume hoods in this room would cause the air coming in from the diffuser to short circuit the room and mean that we didn't get enough fresh air to serve the people. But we had a simulation that was looking at the temperature of the air throughout the space. And so we've said, why not put some people into the space and record the temperatures that they experience and see how they feel as a result. And so we can not only chart the air temperature, but also look at the experience of people on different parts of their body and whether or not they feel hot or cold. And there's a mistake in this image, which we didn't notice until after we'd run the simulation. And that was that we'd accidentally dressed one of the mannequins in the model in shorts. So you see the cold feeling on the leg as a result. We did justify that with the university. We told them that, well, these are students and a lot of them do wear odd combinations of clothing sometimes of the year. So this is just indicating what could happen in that space. We can take this outside as well. So this is a study that we did for the new Sacramento State University. They're developing a new campus. It's about a mile end to end. And so that means that there can be some fairly long walks that people take across that campus. So in this case, first of all, we want to understand where is there access to sunlight. This is going to be a primary source of heat. We did this analysis looking 20 years down the road when we thought that the campus would be full of trees, and also 5 years down the road when there's basically no shade. We also look at patterns of wind. And where do people feel discomfort from the wind, and where is there more shelter because of the structures around them providing sort of a wind wake? And then we take this information together and we plot a path across the site. We say, how is somebody going to walk from the parking lot over to their dorm building in this case? That's it's about a 20-minute walk end to end. And this is even just on a typical, spring day or a fall day, sunny, but not too warm. And we see that there are some areas in the campus where certain people might start to feel hot as a result of the lack of the excess sun exposure. And this starts to give us some guidance in terms of where we should be putting extra shading structures, planting more trees, or providing some sort of respite to help people across this journey. When we're working outdoors, the tools that we're using might feel kind of complicated, running wind analysis with CFD, computational fluid dynamics, or doing solar analysis of an entire site. But the kit of parts that we have to solve those issues are really quite simple. So, if we're seeing that areas are getting too hot, the answer is to put in shading. If we see that areas get cold, the answer might be shelter in order to reduce wind movement. And there are various combinations of those that we can put in to try to create the least complaints about both heat and cold. And we really brought those two considerations together with this project. This is some work that we're doing currently for the city of Providence, where they're taking a few blocks of their downtown that are some sort of disconnected parks and putting them together into an area that would have a more unified and more pedestrian-friendly experience. The landscape architect in this case defined certain activities that people would do in various parts of the park, and we see those activities and immediately we start thinking about metabolic rate. So we have some areas where people just hang out, are doing fairly sedentary activities, some areas that are programmed for more active activities, and then pathways where we expect people to be moving quickly through the site. And we can define thermal comfort requirements for each of those different types of activities. And then, of course, we start to look at a fairly granular level at where we see wind exposure being high, where we see more or less sun exposure, and then putting those together to understand the relative comfort of different parts of the site. And we did this in two ways. One was to look at the ways that wind affected people's thermal comfort, and the other was to look at how wind affected people's active comfort, their willingness to sit down and read a book or a newspaper without pages rustling, for example, or whether or not they can, enjoy a cup of coffee at a bench without the cup blowing over. And so I think what we find here, what we ended up coming up with was a set of classifications that basically said there are some parts of the site that are comfortable for more of the year, and some parts of the site where we see more frequent discomfort. And then the design question, in those areas where we see more discomfort, what can we suggest to make them more comfortable? So where do we reduce wind exposure in order to make people feel warmer in the winter? Where do we increase sun exposure to make people feel more comfortable in the summer? It might be winter too if there are areas that have fewer long shadows on them. And then where do we add shading, which might reduce the feeling of overheating year round? And based on this, we can come back to the architect, and we're not saying that they have to put in a particular solution in any one place, but we're providing guidance to say what makes for a better experience across the entire park. So I'm going to wrap up there, and we've got a few minutes left in which I'm happy to take questions from anyone. And I love having discussions about what makes people comfortable, or hearing your own experiences of what what you might have found to work or to not work in certain instances.
How often do you find that there's kind of like a conflict of where you're putting exhaust and supply ductwork and kind of thermal comfort? Because I remember seeing that map you had of the solar comfort. Um, do you feel like that's a more common issue, kind of ductwork versus solar?
Um, that's a great question, and it's the first thing that comes to my mind when you ask that is a project that they had right when I started at Arup. It was the first project I got on, and the question was this company that had their headquarters building a large atrium, and they'd noticed recently that lots of people had complained about being cold in this atrium. And what we came to understand by doing CFD and tracking down the problem was that there was a door that had been added to the atrium that had been an exit pathway for cool air to return back to the air handler. And by putting in that door and blocking that pathway, cool air was now pooling in the atrium. We were looking at both. So we looked at both cases in the summer when they're providing air conditioning, and we saw that cool air pooling then, and then also in the winter when we expect gusts to be coming in from the outdoors. And it was a very interesting pattern to see. I think it happens more commonly than people expect because in a lot of the cases where it happens, it goes undiagnosed. But one of the real advantages of being able to come in and do this kind of study is we can start to say, there are areas, either whole rooms, or we can get fairly granular and talk about parts of rooms, where exposure to drafts in those locations will be particularly problematic. Um, it also, it does have quite a bit to do with people's clothing as well. I mentioned that draft had been added to the ASHRAE guidelines more recently, and really part of the reason for that was to provide better comfort for women, where the expectation was that women were more likely to have uncovered ankles.
Looks like Amelia Thrall from Ellen Zweig has a question. Do you have recommended set points for winter and summer occupied, standby, or unoccupied?
So I don't think that you'll ever really find someone in thermal comfort come in and say this is the set point that you need to use. And we don't tend to come in and recommend one set point in particular, even seasonally. And that is because we recognize that both individual differences and differences in, even when we're designing around representative occupants, like Asher would have us do, differences in expected clothing level or metabolic rate will drive those considerations. Um, the scale that is most suited to giving you those recommendations is the adaptive comfort scale that was developed at Center for the Built Environment some time ago and is now integrated in ASHRAE 55. And that recommends interior set points based on exterior temperature, based on the morning temperature. So assuming that people dress based on outdoor morning temperature and they carry that clothing outfit with them the rest of the day. Um, you know, that is where that recommendation comes from. What we are realizing now is that people's behavior doesn't really follow that model. They don't really dress based on outdoor temperature. And in fact, the best predictor of how they will dress in the morning is based on the interior temperature that they are exposed to that morning, which means that really the best set point for people to have at work is the set point that they already had at home.
Thanks, Nathaniel. That was a really interesting answer. Hannah, I see you're off camera. Do you want to ask your question? Do you want me to read it from the chat? Happy to ask for you, but wanted to give you the floor.
Sure, yeah, happy to. I was looking online for the tool. Do you have the link to share? Is it publicly available?
Yeah. So the tool is publicly available, but I will warn you, it is down right now because we're trying to move it to a new server.
Okay.
On normal days, you can find it on the web at comfort.arup.com, which I'll put into the chat. But if you click on that link and go to it right now, you will get a 503 error.
Okay, thanks for the heads up. My other question with it was, is there ways in the tool to input your humidity goals? Because I know especially for schools in particular, who I work with, the temperature set point is highly based on what they're trying to do with the humidity in the space.
Mm-hmm. Yes, we take the same inputs that you would expect to get in a typical ASHRAE, which is your temperature, humidity, radiant temperature, and airspeed.
Great.
Any other questions? Don't be shy.
Yes, I have one more follow-up.
Sure.
Um, it's really cool that the tool, it looks like shows the broad range of set points that you might need to consider to meet the different needs of the diverse populations in the space. But in reality, if you have a very diverse and mixed group, does it guide you to, like your case studies were cool in showing some of the, options to actually try and meet those goals. How does the tool help guide you to potential solutions?
It's a great question. A tool that would tell you what to do to solve the problems would be super cool. And maybe with some of these generative AI solutions, we'll be seeing that soon. Um, right now, the tool really just provides guidance in terms of what your current setup um, has produced. I will say though, tend to be fairly intuitive about what's going to increase, make people feel warmer or cooler. So we're, fairly attuned to if I turn down my temperature set point, if I change my humidity, or if I add or remove airspeed, how those will move people. One of the surprising things that we found, though, in putting this together was about clothing and how sometimes clothing can have unintuitive effects on people's thermal comfort. And sometimes the simple adjustments that we might think would work turned out not to work. What's really happening is what I've come to call the anchorman issue. The anchorman is the person who wears a suit from the waist up, and then you don't know it, but maybe nothing from the waist down. And so you figure that outfit has a clo value of 0.5. Well, your typical t-shirt and long pants also has a clo value of 0.5. But the two outfits give you dramatically different levels of thermal comfort. And so one of the early things that we discovered as we were putting the tool together was that people would say, well, I'm just going to make people change their clothing level, and that's going to make them feel more comfortable, and would have the opposite effect. And it was because there were these outfits that might all be labeled as having the same clo value, but in fact were providing insulation around different parts of the body and leading to different pathways for heat to exit the body.
Like David has a question. There used to be an individual desk level fresh air and thermal comfort system. Is there a similar contemporary system that you like?
That's a great question. We've definitely seen a lot of promotion of these systems. And I've tried to put some of them into some larger projects like airports. The pushback, and I think that this is the critical thing to overcome in terms of using these systems. The pushback has to do with maintenance. And if you have lots of systems that are meant to serve individuals and they're all sort of separate or have their own controls, how often are they going to break? And how often are you going to have to do maintenance with that number of small systems put in place? That said, if you can overcome the maintenance issue, they are incredibly useful. As a class, those systems generally will use less energy than trying to condition the entire space. And the added benefit is that each person using them has their own individual control, which means that no one has any right to complain about the temperature because they can fix their own environment. I don't have a preferred system of saying that you should be using one versus another. There are air delivery systems, there are radiant systems, and they all seem to work.
I had a sort of a nuts and bolts question, which was as a practice, um, how does your group integrate with the balance of the engineering disciplines? On typical project, do you find yourself brought in for specific cases, which it sounds like that's the case, or are there attempts to integrate more on a regular basis with mechanical and envelope and sustainability teams to bring some of these ideas into it?
You're right. I mean, typically it is brought in to solve specific problems with buildings. I love it. The earlier we can get into the project, the better, because the guidance that we provide earlier in the project can have more of an impact on the design. What we really try to do in talking with mechanical engineers, for example, is to show them what we can do on these projects so that as soon as there's a question about thermal comfort, the answer isn't, well, we're going to go back to ASHRAE 55 and we're just going to make sure that we're, meeting the guideline, but it's saying, we can open this up to analysis. And the analysis that I showed, especially the stuff coming through the comfort tool, is a really quick analysis. 5 minutes playing around with different settings can get you a lot of information. Certainly, if you want to go into really granular work with computational fluid dynamics, then we're not talking about a 5-minute study anymore. Now we're talking about taking a week to set up a model. But the point that I want to drive home is that this is something that can be accessible to everyone, and you can even give the tool straight to a mechanical engineer and say, hey, you can experiment with these settings and see how, if you adjust the speed of the air coming out of the vent, it's going to change how people feel in that space.
You.
So I think we are at time. If there's any last minute questions, please feel free to utilize the chat or speak up now.
All right. Well, thank you very much. It's been a pleasure being here with this group.
I do have a last minute question.
Sure, Gina, go ahead.
Yes. So usually it is hard to get people, at least in our industry, to do the thermal comfort. So people usually take care about things that directly impact the financial aspect of the project. So if I'm wondering whether there is any way to quantify the impact of these improving thermal comfort to convince our clients to invest in that subject, because it's usually hard for us to get them, aligned with this concept.
Yeah, I think the best way to do that is in terms of talking about how you can relax temperature setbacks. So, for example, we did an airport project where we were looking at the path people took from, entering the airport all the way to their gate. And there is a huge volume of the airport that is just circulation to get you from security to the location that you're going to sit for an hour to wait for your airplane. And it turns out that people don't spend a lot of time there, and so they are not as sensitive to the temperature in that location. So you've got a fairly large volume where you can relax the set point quite a bit and potentially save a lot on conditioning that space and make people more comfortable in that environment. Or not make them more comfortable, but not produce significant discomfort.
Yep. Sounds good. Thank you so much, Nathaniel.
Sure thing.
It was a really great presentation, by the way.
Thank you.